Sir?
Okay, everyone. All right, so last class we started the section on the base. Well, I just introduced you to the first formula, the first shortcut formula that we have for this class, and that was the power rule. And I ended class asking everyone to try a problem. So I'm going to look at this as a bonus. I asked everyone to show me their little picture at the beginning of class. So if you have a camera on, and you want to show me what you got to the camera, I will mark you as being here, and I'll mark you as bonus for attempting the problem. So let's just take a couple of seconds to do that. Okay, everyone got it? All right, I'll keep that on record, and then I'll go back and I'll look at the video and I'll mark whoever put it up there. I'll give you a little bonus on the next test. Okay, so shall we go through it just to make sure you did it right? Let's go ahead and do that. Where's my notes? Here we go. So the problem was this one here, right? So we had an expression that had a fraction in it, right? And what I was really trying to make clear to you is that you have to be very careful that when you're using the power rule, you have to have terms separated by addition and subtraction. You can't have any division or multiplication between those terms. And that's why we can't just do these individually. And so what we did was we put the x cubed over x squared, and then this over this, and this over this. And then we reduce those down to this expression. So what we're saying is that this expression, I'm going to copy it, move it over here. We're saying that this expression was equal to the original expression, right? So this is still the original function. Are there any questions on that aspect of this problem? Everyone comfortable with that? Okay, so now we do the power rule. So we're going to take the derivative of each one of these. And to do that, we will be bringing the powers out front. So we'll get, let's say here, 1, and then x to the, we subtract 1 from the power. So 1 take away 1. I'll just write it down even though we know it's 0. And then on the next one, we have a -4 sitting out here in front. And what I told you last time is that if we have a number in front of the power of x, that will just stay here. And then we multiply by this power rule. So the power is going to come down in front, -3/2 x, and then I'm going to take -3/2, and I'm going to have to subtract 1 from that. And then we move on to the last term. Again, we have a 2 in front, so I'll just write down 2. Bring the -2 out front. So I'll put times, I'll put in parentheses -2, and then x to the -2 take away 1. All right, so that's where we are in terms of the actual mechanical process of using the power rule. The rest of this is just algebra, just putting things together. So we have on the first one, this is x to the 0, which is just 1. So we just get 1 times 1, which is 1. When we multiply these two together, look at that as being a 4/1. So we just multiply across numerator and denominator. We should get plus, what's that, 12/2, which is 6. This will give us 6x. And now we have to do -3/2 minus 1. So whenever you subtract 1 from a fraction, you're going to need a common denominator. So we rewrite 1 as 2/2. And now you can subtract them. So you're just going to take -3 and subtract 2. That'll give you -5 and then over 2. So that's our power here, -5/2. So that's kind of something you should start getting used to, the idea of subtracting 1 from a fraction, because we're gonna need to do that quite a bit in here. So this idea of getting a common denominator is something that you're going to see a lot of. All right, so just get used to it. And then the last term, we have 2 times -2, which is -4. And then the last one, we have to subtract -2, take away 1, we get x to the -3. And that is the derivative. Now you can leave that answer just like that. Or if you'd like, you could rewrite it. If you don't want to have negative exponents, you could take everything that was, every x that had a negative exponent, you could drop it to the bottom. So that would be an acceptable answer. You could also rewrite this rational exponent as a radical. So instead of doing x to the 5/2, you could write that as the square root of x to the 5th. I've got to sneeze. Okay, I'm okay. All right. So you just rewrite the this rational exponent as a radical. So just remember on this, the way this works when you have a fraction as an exponent is that the denominator is what the root is, and so it's a square root. And then the power, the numerator is the power on the x. So that's why I wrote the square root of x to the 5th. And then the last one will just be -4/x³. So all 3 of those answers are exactly the same answers. I would take any of them. I just want you to know when you're doing like your homework and stuff, if you're checking answers, you might see them in different versions. So I just want you to be comfortable with the idea that even though your answer might look like that and the book might look like that, you have the same answer, right? Any questions?
Hey, Professor, is it okay if we did that second part on the side of, on the side for the bonus question?
If you did what on the side?
That second part, that where you show like 1 minus 1, then detect the power and it comes out. Yeah, that part.
Okay. Yeah, that's okay.
Okay, just want to make sure.
Yep. Okay, so to recap from last class, what we established last class is that from here on out, taking derivatives, we're no longer going to use the limit. We're going to have shortcuts. And the first shortcut or the first rule that I gave you was the power rule. And so there's a few other things we have to kind of get out of the way before we can proceed. All right, so let's look at some of the other, what we call basic differentiation formulas. Okay, so the power rule is actually my third formula here. This is the power rule. So I'm gonna actually go back up and show you a couple of others that I could have shown you last class, but I just went right to the power rule. Okay, this first formula says that if we want to take the derivative with respect to x of a constant, so c here represents just a number, that the derivative is always 0. So let me give you a specific example of this. Let's say we have a function f of x equals any constant I can think of. How about 3? Then the derivative of this, according to this rule, should be what?
0.
0.
Yeah, now you can tell if you look at the graph of this function. Now this function here, if we graph it, that's just a flat horizontal line. It just goes through, let's see, 1, 2, here's 3. It's just a graph that goes right through here like this, right? That's what it is. And so if I ask you to go to a point, any point you want, take any, it doesn't matter where you are, and go to the graph and ask you for the slope of the tangent line. Well, the slope of the tangent line will be equal to the slope of the line itself, right? Just flat. And we know that the slope of a flat line is 0. Do we know that? Do you know that? Yes? We should know that. By now, we should all be comfortable with the idea that the slope of a horizontal line is 0. And since it doesn't matter where you go, you're always going to have a flat horizontal line. The derivative will always be 0. And that would work for any constant function. Does that make sense visually why this would be true? Everyone?
Yes.
Yeah? Okay. All right, so that's the first rule. The derivative of a constant is 0. Next rule. Clear. All right, the derivative of x is 1. So that means if we have the function f of x equals x, and we want the derivative, the answer will always be 1. Now let's see if we can't justify this with a picture. So what does the function f of x equals x look like? Well, if you go back and think about college algebra, that was what we called the identity function. It's that function that's just a perfect diagonal. This is like 45 degrees here. And if we go to any point on this one, and we ask, what's the slope of this tangent line? Well, the slope would be 1, okay? Because the function itself is pitched at 45 degrees. That means the rise over run is the same, no matter where you are. So that's why the derivative of x should be 1. Now, you can also use the power rule, okay? But the way I did this in these lecture notes, power rule comes next, so you wouldn't know this if I were going in this order, but because I've shown you this already, we can actually show that this also works with the power rule, because we know that the 1 here, if that's the power, then when we take the derivative, the 1 comes out, so we'd have a 1 in front of x, and now we take 1 and subtract 1, we get 0, and x to the 0 is 1, so we wind up just getting 1, which matches this answer, okay? But this is just a visual representation of why that's true. Any questions there?
No, sir.
Okay, thank you. All right, so now the next rule is the power rule, and that's the one from last class. And you know, we've done enough of these, but I'll just throw an example down here. Let's say we have I don't know, x to the 7th. This rule says that the derivative of this should be, well, we bring the 7 out front, we take x, we subtract 1 from the top, we get 6, and that's it. Now, I cannot show you this visually, okay? The reason I can't show you this visually is because powers of x can look like different things. So there's no way I can like show you a general picture to convince you that this is true. The only way I can convince you that this is true is by doing what I did last class, which is going through the actual proof of it, which took us doing what, the Pascal's triangle. Didn't we do all that? Yeah.
Yes.
So that's the only way I can prove to you that the power rule is correct. Okay, so you're just going to have to now take this on faith that the power rule holds. Well, no, it's not on faith. I showed you. So you're just going to have to understand that this is true. Any questions there?
No, sir.
All right, what did I do there? All right, so what comes next, right? I bet you're all excited to figure out what comes after the power rule. Well, it's this rule. It's called the constant multiple rule. Now, we have used this rule, but I hadn't given it to you formally, all right? So the way I'm going to illustrate this rule is by asking you to compare two things. So let's say we have a function f of x equals 4 versus the function f of x equals 4x cubed. And I ask you to find the derivative of each one of these, right? So we have two different functions. Well, the first one, we have f of x is a constant, right? And that constant is by itself. Do you all agree? There's no x's there. So what is the derivative of a constant?
0.
0, always 0, right?
Yep.
On the next one, though, on this one, we have 4, but it is attached to x cubed, right? It is multiplying x cubed. And whenever you have that, you do not follow this rule that the derivative of 4 is 0. What you do is the constant multiple rule, which is when you take the derivative, you just bring the 4 along for the ride. Okay, that's what I always say whenever I'm doing this. 4 just comes along for the ride. That's all it does. It comes down, and then you focus your attention on this piece, and you do the derivative of that, which in this case would be the power rule. So we bring the 3 out front, and we subtract 1 from the power. And then we just multiply 4 times 3 and get 12. Do you all see the major difference between those two? Constant by itself, derivative is 0. Constant attached to a function, the constant comes for the ride. Yes? That's what this is saying right here. If you take the derivative and you have a constant times a function, what you can do is bring the constant along for the ride and then go ahead and take the derivative of that thing that was next to it. That's what the rule's saying. By the way, I could prove all these rules, just like I proved the power rule to you. I could prove all of these using the limit, but it would just take way too much time in this class. All right, so I only showed you the proof for the power rule. I don't think I'm going to show you any more proofs. They'll just take too long. If you're interested in them, though, you can come to my office hours. I'd be happy to go through those proofs. All right. Any questions? I'm going to move on.
What about if is like a sine function like a constant, like, you know, like when it's like
Yeah.
sine of whatever, I forgot, like sine f, I mean sine 4x or something like that, and
Yeah,
that comes along for the ride?
So you're asking, what if we had a function like this, sine of 4x?
Yeah,
What would
something
the
like that.
derivative of this be? Right now, I
Yeah.
would just have to tell you, stay tuned, because we don't know how to do this yet. This is
Okay.
going to require the chain rule, which is not yet.
Fantastic.
So we have from here, we're going to go our basic rules. After we get our basic rules, then we have what's called the product rule and quotient rule. After we have product rule and quotient rule, then we talk about the all important chain rule. And that's what we would need for this. So just stay tuned. We'll get to it.
Oh, okay. It's in a function inside of a function. I see now. Okay.
That's right. That's a function inside of a function, which means that you need the chain rule. Okay, the next rule has to do with something, again, that I've already told you you can do, but I never formally said you could do it. And that is this. Let's say you have a function that has multiple terms in it. Okay, so like x squared, let's say plus 3x, let's say minus 5x to the 4th. I'll do one more, plus 7.
Isn't it
Guys-
the one we just did as a bonus one, kind of same?
Yeah, I mean, this is pretty much like the bonus, but what I'm doing right now is I'm formally giving you the rules. Okay, so that way we don't take anything for granted. We understand that each one of these can be proved to be true. And so now we can use them. So this rule says this: if you have addition and subtraction between two things, so don't look at this as f of x and g of x, just look at that as just some expressions. If you have addition and subtraction between two things, that if you want to take the derivative, then you can split them up and take the derivative of each one individually. So that's why I told you when you want to find the derivative of this, I said, because there's addition and subtractions, we can do the derivative of each one of these separately, right? That's what I told you we could do. And now this rule says formally, yes, that's okay, all right? So to do this, what I would do is I would say, all right, well, first let me take derivative of this. Well, that's power rule, right? 2 comes out, subtract 1 from 2, you get x to the first power. How about this next one? Plus, how about this? 3 is in front of the x, right? So does the derivative of 3 go to 0, or does it come for the ride?
It's gonna be 3 itself, and then wouldn't the next one be minus 20 x to the third, and then the 7 doesn't.
Hold on. My question is the derivative of 3 0, or does 3 come for the ride?
3 comes further.
The ride with the X, right?
It comes for the ride because it's attached to the X. So when I go to take this derivative of this whole thing, the 3 comes for the ride. And then the derivative of X, what did we just say a second ago? The derivative of X was? 1, right? So this is 3 times 1. Okay, now I'm with you, Danielle. So now minus, now here again, the 5 comes for the ride. And now the derivative of X to the 4th would be power rule. So 4 comes down, subtract 1 from the power. And then we do plus, and then the derivative of 7 is
Nothing.
nothing. So in this case, the derivative of 7 is 0 because 7 is not attached to a function. It's just 7 by itself, so its derivative must be 0. And then we can do a final cleanup, 2x plus 3 minus 20x cubed. So again, all I'm showing you right now is that you are allowed to do this. You are allowed to do addition and subtraction individually. We call it term by term differentiation. Each term we differentiate each term. We just go term by term. Questions on that?
Couldn't you say that like you're taking the derivative of this of number 7 of the plus 7 because it's a constant and it would just be 0 anyways, right? Like, aren't you
I'm
taking?
not sure what you're asking me.
Like you said, the derivative of a constant is 0, so then 7 is a constant, so it's going to be 0.
Yeah, that's exactly what
Right.
I'm saying. Mhm.
Okay.
Yep. Any other things? Okay, so now we get to something a little more difficult. And that is, what is the derivative of the sine function? So I'm telling you what it is right here. The derivative of sine of x is cosine of x. All right, this is weird. Okay, let's take a look at this. Where's my thing here? Give me a moment to bring my graph up. Okay, so what we're going to do is we're going to look at the graph of sine of x. And then I want to look at the graph of cosine of x. And I'd like to make this dotted. Yeah, there we go. All right. So the red is sine. Okay, the red is the sine function. And the blue is its derivative, which is cosine. Let's try and convince ourselves that this is true. Right? I'm going to try and convince you visually right now that the derivative of sine is cosine. So I'm trying to show you right now that when you take the derivative of sine, you get cosine. Now, let's look at this first point at 0. Would you all agree that at that point, the slope of the tangent line on the sine function looks like it's a perfect diagonal, which means the slope would be 1. Y'all agree with that?
Yeah.
So that means if I'm plotting the derivative, it would be a value of 1. And then as I move from left to right, look what happens to that slope of the tangent line. It's still positive, but now do you see it starting to flatten out? So as we move from left to right, the derivative of sine is positive but starts to flatten, which means that it's a positive number that starts to get smaller. And then once we get to this point right here, what is the slope of the tangent line there?
0.
Right? Which means the derivative, which is the blue one, needs to be 0. And so right here, from here to here, that blue represents the fact that our derivative was positive, but getting smaller and smaller and smaller until it got to 0. And then when you get to the other side of sine, the tangent lines are now negative, aren't they? These are negatives until you get to this point right here. That's where you have a perfect diagonal, which means that your derivative is at -1. Until you get on the red function to this bottom point, and that's where your derivative is 0 again, which corresponds to that dot. So we've done this before where I gave you a picture of a function. I asked you to graph its derivative. And I said, for some of you, this is going to be a light bulb. It's going to make sense. You're going to see the connection. and for others, you're going to struggle to see the connection. If you haven't seen the connection between a function and its derivative, then what I'm doing right here is going to be like not making a lot of sense. So if you have a question, now would be a good time. If you need me to explain why this blue graph is doing what it's doing. No?
I just have a question for the one for cosine and its derivative being negative sine x. That's all.
Okay. Well, yeah, we'll get to that one. That's going to be next. Okay, so this is now something you all need to know, all right? Everyone here needs to know that the derivative of sine of x is cosine x. And now we move on. The next natural question would be, what's the derivative of cosine, right? Is the derivative of cosine of x sine of x? Maybe, I mean, it seems like it might be. So I'd like for you to now kind of reverse your thinking. Let's do the cosine x here in red, and we'll do sine x. Well, let's not even do anything. Let's not do anything at all. And let's see if we can't draw the derivative of cosine. This is cosine. Let's see if we can draw its derivative. So I'm going to go to some important points. At this point, oops. Whoa. Okay. At this point right here, the slope of the tangent line would be 0, wouldn't it? Which means the derivative must be 0. Also here, at this point, the slope of the tangent line must be 0, which means the derivative must be 0. Here, at this point, the slope of the tangent line must be 0, so that means the derivative must be 0. So far, this is what the derivative looks like. So how about between this point and between this point right here? Somebody tell me about the derivative. What's the derivative doing as I move from here along this curve?
It's going down negatively.
So
Right.
it's negative, right? The slope is always negative. This is going to be negative, negative, negative. It looks like when we get to about here, that slope is going to be like a perfect diagonal, which means it should have a slope of -1. So that means that the derivative should have a value of -1. And then everything between here and here, between and here, the derivative should be negative values. So it should be negative and then get to -1. And then once you start going this way, that slope of that tangent line starts to flatten out again until it gets to 0. So we have negative numbers back to 0. Once you get to the right of this point, now we have positive derivatives, right? So the slope of the tangent line is pointed up. Here we should have 1, +1. So positive numbers going up to +1. And then those derivatives should start flattening out again and getting back to 0. So we should go back to 0. So is the blue function the sine function? It's not, right? Look, if I think I just messed up everything. So let me graph sine x. Move that back. Okay. Yeah, that worked okay. So here is sine of x, the dotted one. Our blue one is not sine of x, is it? But doesn't it look like it's sine of x kind of reflected over? Like just reflected over the x-axis? And that, in fact, is what it is. So if I change that to negative sine x and put that back, you can see that the dotted one and the one we drew are exactly the same thing. So that's the main takeaway here, is that if you want to know what the derivative of sine of x is, it's cosine x. That's what we established before. But now the derivative of cosine of x is negative sine x, not positive sine x, but negative sine x. You need to hardwire that into your brain, all right? Let me just do two quick examples. Let's say we have a function f of x equals x cubed plus 5 sine x. Let's do another example. Square root of x minus 3 cosine x. All right, let's try these. Let's try and find the derivatives. So on the first one, I'm going to call on somebody here. How about Matthew? Matt Gutierrez?
Yeah, I'm here.
Okay. Can you help me out with this first one? What's the derivative here?
So you would bring the 3 down into the front of x,
Okay.
right?
Yep.
And then you put the x, and it'll be 3 minus 1, which is 2.
Okay, good. All right. So now you just decided to do this one by itself, right?
Yes.
And that's because I told you in a rule that if you had addition and subtraction between, you could just do them individually. So that's what you're doing, right?
Yes.
Good. Okay, now on this one, you're gonna take derivative of this. So tell me about the 5. What are you gonna do with the 5?
You're going to bring it down.
You're gonna bring it down. Now, why is the derivative of 5 not 0?
Because it's attached to something.
It's attached to a sine of 5 or sine of x, right? So that's why it comes for the ride.
Mhm.
Okay, go ahead, keep going.
And then the derivative of sine x is cosine of x.
Cosine of x. There it is. Done. Everyone got that? Good, Matthew. All right, next victim is going to be Laura. Is Laura here?
Yeah, I'm here.
Okay, Laura. You get the next one.
Well, I know the square root of x, you could write that as x to the 1/2.
Good.
So it would be 1/2 x negative 1/2.
Good. So what you did is you took x to the 1/2 and you subtracted 1. So you had to do 1/2 minus 1. And that 1/2 minus 2 over 2, which meant 1 minus 2 over 2, which is negative 1 over 2, which is negative 1/2. I'm just showing all the work there, but yes, you did that perfect. Okay. All right. Next step.
And then I would bring the -3 down.
Okay. Very good. Because it's just attached to a cosine function, so it's going to come for the ride. Go ahead.
And then you would multiply that by negative sine x.
Good. I'm glad you said multiply because you have to be careful here. We're multiplying by the derivative of cosine, which is negative sine x. What you don't want to do is accidentally write this down because that looks like 3 minus sine x, doesn't it? And that's not actually what we have. It's 3 times negative sine x. So what we can do is take that negative out to the front and make that a plus. That all right with everyone? I'm going to do something else. I want you all to pay attention to this. I'm going to rewrite this. I'm going to pull this x to the negative 1/2. I'm going to drop it down to the denominator, make it x to the positive 1/2. Now I have a plus 3 sine x here. One more thing I'd like to do. X to the positive 1/2 really means the square root of x. So I'm just going to rewrite it that way. So I'm just showing you another way of writing this answer would be to look like this. Questions on that one? Sure.
Both answers are acceptable, right? If I was to put 2x to the 1/2 or the other one. Okay.
Yep, they're all equivalent, right? Algebraically, they're exactly the same. Now, let me take a moment here. I want to do something real fast. All right, so I'm starting a new page because I want everyone to remember this, all right? As long as I've been teaching calculus, students will take this and they'll do this. And then if we take the derivative, they'll say the answer is 1/2 x to the negative 1/2, which is true. I agree with you 100%. But this turns into what I just did, 1/2 x to the 1/2. And that turns into 1/2 square root of x. Right, that I just showed you that algebraically, right, a second ago. Here's what I'd like for you to burn into your brains as quickly as possible. The derivative of the square root of x is 1/2 root x. That's this answer, okay? Memorize that. If you want to take the square root of the derivative of the square root of x, it's just 1 divided by 2 of those square roots of x. That's the formula. Now, I'm saying, even though this is correct, your life will become much easier in this class if you can memorize it this way. All right? All right, let's move on. All right, let's move on. We've got more to do here. Y'all ready for spring break? It's coming. It's coming.
Lots of work.
Okay. So here's what we have right now. We know derivative of a constant by itself is 0. We know derivative of x is 1. We know that derivative of x to a power, we apply the power rule. We know that if we have addition and subtraction, we can split them up. We know that if we have a constant attached to the function, the constant comes for the ride, and we just take derivative of the other part. We know derivative of sine is cosine. We know derivative of cosine is negative sine. We don't know what the derivative of tangent is, though, right? That we don't know yet. We don't know. So I'm going to tell you what it is. And for now, you're just going to take it on faith. All right. You're just going to be like, okay, he's telling me that's what it is. That's what it is. I'm not going to argue. I'm not going to ask why. All right. And then in a little while, maybe not today, but maybe when we come back from spring break, I'll show you why it is. So the derivative, and actually, I'm going to give you for all 4 of the remaining trig functions. So remember, in pre-cal, there are 6 main trig functions, right? Sine, cosine, tangent, cosecant, secant, cotangent. There's 6 main trig functions. Each one of them has a derivative. Sine and cosine I've given you. Now I present to you the other 4. And you need to memorize sine, cosine, tangent. Those you should just have like ready to go off the top of your head. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Those should just be like just rolling off your tongue. The other 3, if you can memorize them, great. If not, you need to know where to get the formulas for them, okay? And if you need to look, all these formulas are on your formula sheets. They're on reference page 5. And you will see that we've actually done a lot of this. The derivative of a constant is 0. The derivative of addition, you can split it up. Don't worry about that. We haven't done that. We haven't done that. Here's the constant multiple. If you have a constant, you can pull it out in front. If you have subtraction, you can split it up. Don't worry about this yet. We haven't done quotient rule. So we haven't done product rule, chain rule, or quotient rule yet. We have done the power rule. But if you scroll down a little further, it says trig functions. It shows you the derivative of each one. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared, so on and so forth. Know that that's where they are, but you need to memorize the first 3. I will get angry with you if in like 2 weeks after we come back from spring break, I ask you what the derivative of tangent is, and you're like, I won't get angry. I don't know what I'll do. I'm just trying to get you to know that I expect you to know that. All right. All right. Here we go. Those are the main basic differentiation formulas from this section. So at this point, there's a lot of other new things we can take the derivatives of, right? There's a lot of things now that we can say, hey, what's the derivative? And we can go figure it out. No limits, right? There's no limits involved. So this is very powerful. These rules are very powerful. So this is time to move to the next section, all right? And I think what I'll do is I'll motivate this with a question. So we know what the derivative of these are, right? I know what the derivative, well, you should know what the derivative of this is, right? And if I give you a different function like this one, like sine of X, individually, you know what those derivatives are, right? Derivative of X, 1. Derivative of sine, cosine, right? So those by themselves you could handle. So f prime of X here would be 1. G prime of X here would be cosine X, because that's what I said. But let me ask you this. What if we had a function that was both of those functions not added together, but multiplied together? So X times sine of X. What would the derivative be, right? So someone who has not done this before and doesn't know where I'm headed with this, somebody tell me what naturally they feel like the answer should be.
Cosine of X.
Just cosine of X. So that would be, you look at the X and you say, okay, what's derivative of X? You say 1. And then you say times, right? And then what's the derivative of sine of X? And you say cosine of X. Are y'all paying attention?
Yes, 100%.
All right. This is very important because if it were this way, if this is the way it was, calculus would be easy. But I've got terrible news for you. This is not the way it is. All right. When it comes to taking the derivative of a product, okay, if this is a product right here, right? This is multiplication. When you have a product between two functions and you go to take the derivative, you are not allowed to take the derivative of each one individually and then multiply the answer. You can only do that if it's addition or subtraction. All right? Which begs the question, then what do you do, right? Like how do you take the derivative then? And so I now present to you the product rule, all right? And this product rule, I'm telling you this product rule is what makes calculus suck. This is what makes it so much harder than it could be, is that if it wasn't this way, if it was like this, okay, and by the way, I need to say that's wrong. If it was like this, then man, everyone would be like, calculus is easy, but it's not. So here it is. You ready for it? Here's what the product rule says. If you're given a function times some other function. So notice I'm just calling it f and g. I could have written this way. I could have written it this way, but I'm just going to, instead of writing f of x and g of x, I'm just going to write f times g. If you have that, then you want to take the derivative, right? You want to know what's the derivative of that product. Here's what it is. It is the derivative of the f function. So it's going to be the derivative of that first function times the second function g, but don't take the derivative of g, just g by itself. And then add to that the derivative of the g times the f without the derivative. And that is the product rule. Now, again, I could prove that rule to you, just like I proved with Pascal's triangle. I could prove this rule. It's a beautiful proof. But again, it's just too much time. I would eat at least 30 minutes doing it. And I think it's more important for you in this class to just start using the rule and seeing how it can become pretty messy. All right? Okay, any questions before I begin? I'm going to go to that example.
I have a question.
Yep.
Oh, I have a question. It's kind of related, but what's the difference between a theorem and an algorithm?
A theorem is a proof of a statement, proof that a statement is true. So let's say you make a statement, right? Like I say that, you know, all kids under 5 years old are brats, right? Then I need to prove that somehow. So a theorem would be me saying, hey, all 5-year-old kids and younger are brats. And then the theorem would be the proof of that, right? So I'd be able to prove that that's true. That's a theorem. That's a terrible example, but okay. Now, an algorithm is a procedure. It is a set of steps that allows you to execute some operation. So like when you go to your calculator and you type in like sine of 30 degrees, inside the calculator, there is a program that it takes the input and it goes through an algorithm, a set of steps to arrive at an answer, a numerical answer. Does that make sense?
Yes, thank you.
Okay. That was truly random, but I appreciate the question. Okay, so we need to try and find what the derivative of this is, all right? So the first thing you need to notice here is that you have a product, okay, everyone? You have a product right there. You have to see that. Okay, now in the original question, I did put a dot there, but the way I'm presenting this right now, I'm not going to put the dot there. because I want everyone to understand that that is implied that that's multiplication here. Also, I should point out that this x lives in the sine function, right? This is sine of x, right? That's not multiplication between that sign, between the letters sin and x. That's not multiplication. This is sine of x times x. We good with that? Yes? Okay, so what I like to do, and I've been doing this forever, is I like to draw a dotted line between the two things that are being multiplied. And then I just figure out what I'm going to call each one of these. So I want to use this formula, and I'm going to kind of label, this is going to be my f, and this is going to be my g. Forget the fact that this whole function is called f. I'm just calling this f and g so I can use the formula. All right? So here we go, derivative time. According to the formula, the derivative of that should be, I'm going to write it above it. So I'm going to write this formula right above this blue line so I can follow it. It should be the derivative of f times g plus the derivative of g times f. Okay, that's this formula right here, just written kind of above where I'm about to put the answer. So let's see here. Dilpreet, you're up.
It's gonna be 1.
Okay, so now Dilpreet's following the formula. It's going to be 1. That's derivative of f, which is derivative of x, which is 1. Go ahead, times.
It's gonna be sine of x.
Sine of x. Why didn't you take the derivative of sine of x?
Because it didn't say in a formula.
That's right. The formula said don't take the derivative of g. Not yet. Now keep going.
Plus,
Plus.
derivative of sine of x is cosine x.
Now you're doing it, right? Cosine of x. And I'm going to put that x in parentheses and then keep going.
And it's gonna be x multiplied x.
Times the f function without the derivative, which is x. Okay, so the way you can look at the product rule is that it's like if you have a product and you want to take derivative, the product is going to like take turns. Like first it's going to take the derivative of the first one and leave the second one alone. And then you'll have plus, and now it'll take derivative of the second one and leave the first one alone. Do you all see how that's working? And again, don't ask me why it's that way. It is that way. The proof is too long for today, but that's it right there. Okay, so now here's what we have. 1 times sine of x is just sine x. And then over here, when I multiply those two together, remember that x cannot go inside with that cosine. So I'm just going to leave it on the outside. I'm going to put that x out in front of this cosine, and that will be my derivative. And that is it. I think it's worth looking at. I'll leave that up for another second or two. So what I'm going to do here is I'm going to go back to this thing. I'm going to graph the original function, x times sine x. No, that's not times. X times sine x. Okay, the red function is x sine x. Pretty cool looking function, right? And now I'd like to graph the derivative of that, which it should be sine x plus x times cosine x. All right. So let's see if this blue graph really does represent the derivative. So the first thing I'm going to do, I'm going to go to the red function. I'm going to go everywhere I see a flat horizontal line. Here, here. You know what? Let me zoom out a little bit more. Sorry. There we go. So here I have a flat horizontal line. Here I have a flat tangent line. Sorry, flat tangent line. You have a flat tangent line. So anywhere I have flat tangent lines, the derivative should go through 0. So my derivative should be 0 here. It should be 0 here. Oh, I missed one. 0 here. 0 here. I missed that there was a flat tangent line right there. So I should have 0 there also. And do you all agree that blue dotted one seems to do that? Right? Further, if I start looking at the slopes of the tangent lines, let me look like in this section right here. In this section, I should have a positive derivative that starts at 0, goes positive, and then goes back to 0. And that's exactly what is happening. It starts positive and goes back to 0. Starts at 0, goes positive, back to 0. And then between here and here, my derivative is negative, 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 and then it goes back to 0. And that's exactly what this does. Okay? So hopefully you see that. If you don't freak out. But it works. Let me show you, just to try and convince you, let me show you that what you wish it would have been. So we wish the answer just would have been cosine x, right? Because then it would just be take derivative of x, you get 1, take derivative of sine, you get cosine. So our answer, maybe in a different universe, in a different parallel universe, this is the way it would work. But you can tell right now that this won't work, because if, again, we go back to where we have flat tangent lines here, right? Our derivatives should be 0 there. But if you look at the derivative, it's not quite. It's like right here. And then on this one, it's like down here. And then this one, yeah, this one right here, it's up here. It's just, it's not matching up. Do y'all see that? It's like that cosine x is just not matching what it should be. And that's because it's not the derivative. All right. Your turn. I'm going to give you one now, and I want you to see if you can work it. All right, here we go. I'm going to do y instead of f of x just to try some different notation here. Okay, I'll give everyone a minute or two. Go ahead and look at that. See, oh, and I need to tell you what to do. Find y prime. So find the derivative. Go ahead. Do you want the formula up here? I can put it up here. I'm going to put up a poll. I know not everyone can take the poll, but I'm going to put a poll up. Let me know when you're done. If you finish that one, I'll give you another one. Just let me know when you're done with the first one on the voting. Thirty seconds left. Okay, that's time for at least the first one. So let's see, I'm going to call on somebody here. Is Carla here?
Yes, I'm here, sir.
How's it going?
Good, thank you.
Good, good. How about the first one? You get it?
Yes, I did.
Okay, so I'm just going to ask you to read it out to me.
Okay, so y prime equals to 3x squared times tangent x plus x cubed secant squared x.
Perfect. Good job. Okay, does anybody need me to clarify that? Or go through that in any more detail?
Can you please?
I can, yes. So we looked at a product right here between these two. We call this F and we call this G, right? And now we follow the formula. So what we need is F prime times G plus G prime times F. So Claire, since you asked, what is derivative of F?
3x squared.
3x squared, so I put that down, okay. And then what is G?
Tan x.
Tan x, okay. And now plus, now what's the derivative of G?
Secant squared x.
Squared x, good. And then times
X.
F,
cubed.
which is x cubed. Now, again, you cannot put these two together, okay? That does not become x to the fourth. You have to be careful with that. That x that's in the secant is trapped in there. And so that means, who was it? Carla decided to move that x cubed out front, which is good. I like that. Because then students don't get confused. They don't accidentally try and put those together.
Oh,
That makes sense, Claire?
yes.
Okay.
So since x to the cube has a higher power, do you want to put like the highest to the lowest power?
Not really. It's not about the fact that that power is higher. It's more about the fact that I don't want to write x next to x cubed and have people think that they go together.
Okay.
So to be safe, we pop the x cubed out front.
Got it.
Okay. All right. Does somebody want to tell me the second one? Someone want to read out the second answer?
So, oh, go ahead.
Go ahead.
Oh, I just, I don't know if that's right or wrong, but I didn't know if I should put cosine squared x or cosine x squared and then minus sine squared x, or if it's sine x squared. So I didn't know
Gotcha.
which one it,
Well,
I didn't know which one to put it.
let's go through it slower. How about this? How about we just go through like one step at a time? Okay. So what is F prime? So did you split it down the middle, call this F and call that G? You're muted.
Sorry, I wrote down cosine x times cosine x plus negative sine x times sine x. And that's from there where I'm just like, okay, so I have the thing there. So I don't know if I put the squared on the cosine or if I put it on the x, but then I could move the two over in the front as it's like, you know, I have a lot of stuff going on in my head, so I don't know which one to do.
Okay, so
Oh,
F.
times sine x, my bad, at the end.
Yes, but I thought you said negative. So, okay. Derivative of F, derivative sine of X, cosine X, and then you bring the cosine, plus derivative of cosine, you said is negative sine, and then you said times sine X again?
Yes.
Okay, yes, that's correct. Now we have this plus minus that looks weird here. So just remember, this is really like, you know, that negative sign is just going to turn this plus into a minus. So the way I would write this next line is, since you have cosine of X times cosine of X, that could be written cosine squared X. That's the notation we used in pre-cal. And then we have a minus here. And then sine X times sine X, we'd write sine squared X.
Woo! All right.
Good. That's almost one, right? If that minus were a plus, the answer would be 1, wouldn't it? Because the Pythagorean identity says sine squared X plus cosine squared X is 1. But because it's subtraction, that's our answer, okay? That's it.
So when would do we ever grab that squared and put it to the front at any point? I like in another type of problem, because I feel like
Yeah, that'll be chain rule. That'll be chain rule later. Yep.
Okay, then I just trying to get my thoughts together.
Okay, I have another one for you. All right. So let's just talk about this first. We have a bunch of x's to powers here, right? And then we have them in parentheses, and then we have a bunch of other powers of x, and then a constant by itself, but we've got all this multiplied together. Is everyone clear that we have multiplication between these two? So one thing we could do is we could actually like expand this out. We could just do algebra, do this times this, this times this, this times this, times this, then do this times this, this times this, this times this, this times this, and then that, and we can multiply everything out. And if we did that, we'd have this big long expression with just pluses and minuses between them. And we could differentiate them one by one, couldn't we? We could, but because this is a product, I can treat this entire thing like f and this entire thing like g, couldn't I? And then just do the product rule. So let's do that. All right, so I'll put above this what it is. It's f prime times g plus g prime times f. And we will go with, let's see here. Daniela Silva. You here?
Yes, I'm here.
Are you following this today, Daniela?
Yeah,
Okay.
I think so.
All right, so let's go then. What would the first part of this be then?
So I have to put like the power of
Mhm.
x.
So you
in
have
front
three
of
of these here, right? F has 3 terms. You can do them one by one. So let's go through them
Okay.
one by one.
Okay,
First
so it
one.
will be x
2x, okay, plus derivative of x,
it will be 1.
1, okay, plus derivative of 3.
It will be 0.
0. So I'm not going to write
Like
anything,
if I
right? I'm just going to put
Okay.
2x plus 1. Now that's f prime. Does everyone agree? That is f prime only. And I now need to multiply it times g. So I need to put this in parentheses because I have more than one term there. And now comes g. Now g is everything here, right? No derivative, no derivative. So x to the 4th minus x squared plus 3x minus 4. Boom. Daniela, what comes next?
it will be 4 x.
So I'm gonna put the plus sign, right? Make sure we put this plus sign here, right? And now go ahead. You're gonna give me the derivative of g. Go for it.
Okay, it will be 4x. Yeah, to the
third power.
3.
Okay. And on this one,
And minus 2x.
yep. And then derivative of 3x.
It will be just 3.
Good, good job. Okay, and then the
Plus
derivative of -4, which is
0. It will be
0.
like nothing.
Nothing. So we'll just leave that, right? This is g prime. This is derivative of g. So I'm gonna put that in parentheses. And then we still have to multiply by f. And f is everything that was out here with no derivative on it. There it is. That is our derivative, right? Nobody said it was going to be pretty. That's what it is, all right? Any questions? You can leave that answer. That's okay. Later on, we're going to have to do some algebra with this, but for now, this is just this is all.
So we're just leaving it like that, or can I try and give a final answer?
This is fine. This is okay. See, remember in the beginning, we could have distributed, right? We could have done like expand that all out, but we avoided it by just doing product rules. So let's not expand our derivative out either. Let's not try and multiply all that out and do all that and then do the same thing. Let's just not do that. All right, good. I think you're kind of getting the hang of it. Yes, y'all feel like you have some idea. All right, well, see if there's any others I would like to do. No, I think we're ready to move on. Yeah, let's move on. So when I first started this idea of the product rule, the motivation was that, okay, if we had X by itself, we could take the derivative. If we had sine by itself, we could take derivative. But if you multiply them the two together, I told you are not allowed to just take the derivative of each one and give me that as an answer, multiply together, right? So let's try this. What if I give you a function where I give you X, but on the bottom, I give you sine X? In some parallel universe where math is easy, the derivative of this would just be 1 over cosine X. Do y'all see what I did there? Just took derivative of the top, got 1, took derivative of the bottom, got cosine. But that's where you wish you lived. You don't live in that universe. You live in the universe where that derivative doesn't work that way, okay? Just like the product didn't work that way. Now, again, I can show you the proof, but I'm not going to. So let me give you the new rule, okay? Instead of a product here, we actually have a fraction, which is called a quotient. So we have this thing called the quotient rule. And here's what the quotient rule says. If you have some function f, and instead of being multiplied, you're dividing by some function g, and you'd like to know what the derivative of it is. So do y'all see that that's basically the product rule? But instead of f times g, I'm doing f divided by g. Y'all see that? Okay, so this rule says if you have f divided by g and you want the derivative, here's what it is. You ready for this? It's the derivative of f times g. I'm not done, okay? Minus the derivative of g times f. Does that look familiar?
Yeah, same with the last one, but a
Yeah.
different sign in between.
Yeah, this is isn't that the product rule, but with a minus instead of a plus? Right? That's all it is. But there's one more thing, okay? And this is like, you won't expect this at all. You have to take that entire answer and divide it by g squared. So it's like you're going to almost do a product rule, but make it minus instead of plus. And then once you're done with all that, you'll divide by g squared. That means g, don't take the derivative of g, just take whatever g was and square it. So let's do this problem. Let me let you try and do it first. Why don't I give you a minute to see if you can find the derivative of this? Take f of x equals x over sine x, and I want you to find the derivative of it. And I'll give you 2 minutes. And I'll do the poll again when you're done. Go ahead and say you're done.
Hey, professor.
I'm sorry, can you repeat that?
Yes, actually, I was saying since it's a g square, right? And it's a sine of x, so will we write down sine square x or, right?
Write down what you think it is.
Okay.
You're on the right track. Just go with what your gut's telling you and we'll talk about it. If you get that one, I have another one for you. I want you to take the derivative of tangent x, but you're not allowed to use the fact that you know that the answer is secant squared. Okay, so I want you to think about it. You're not allowed to say, oh, the derivative of this is just secant squared. You need to somehow figure that out on your own. And the hint is that you can do it with the quotient rule. And I'm still waiting on other students to finish the first one.
Said he wanted us to use the quotient rule for that second one.
I said that would be a way you could do it. That's my hint to you. Okay, that's a majority of you have finished the first one. So let me ask someone to share their answers. Axel with us today? Axel. No Axel. Okay. Oops. How about Benjamin?
It should be sine x.
You're just going to give me the answer? Is that what you're going to give me for that one? You can go through it piece by piece. That's fine. Go ahead and tell me.
For piece by piece, f prime.
Yeah,
should
f
be
prime.
Should be 1.
Good.
Times sine x.
Good.
Minus cosine x times
Good.
x.
Perfect.
All over sine squared.
X. Excellent. That's it. Does anyone have a question on where that came from? So Benjamin was treating the x up here like the f, and then the sine x was like the g, and then was just applying this formula, plugging in the different pieces. Now we could try, and there's not a lot we can do to clean this up. We could do sine x minus, we could move that x in front of the cosine x, and then divide by sine squared x. That would be a nice looking answer.
You can't do anything with the sine x and the sine squared x, right? Like subtracting or anything like that. You can't do it.
No, the only thing that you could do if you wanted to is you could take the sine x and divide it by the sine squared x, so split it into two fractions, minus
right.
the x cosine x over sine squared x. You could do that. Then this one would become a 1.
Right. Okay. Yeah.
Sorry, 1 over sine x, not that'd become 1 over sine x. You could do that. Minus, now check this out. If you're going to go that far, then you may as well do this. Cosine x over sine x times 1 over sine x. You could do that. So notice I have a cosine here and I have 2 sines. So I could put a cosine on top of one of the sines, and then I could put a 1 on top of the other sine. And then I could rewrite this way, cosecant x, because that's what 1 over sine means, minus x, and then cosine x over sine x, pre-cal, that's cotangent x.
Mm-hmm.
And then 1 over sine is cosecant again. So that would be another way to write that answer.
Okay, because I was wanting to break it down just like that. And I was like, should I be doing that? Is that legal? Because I was breaking it down.
Yeah, you're allowed to. Now, I'm okay with this answer for now, because where we're headed with this, we're going to be setting this equal to 0. So it's easier to work with this than this. Okay, now on the second one, the way you go about this is you can just rewrite tangent of x as sine over cosine, and then treat the top like f and the bottom like g, and then do your quotient rule. All right, so I'm going to do that real quick. If we do the quotient rule here, I'm going to go derivative of f, which is cosine x, times the bottom g, which is cosine x again, minus, now here's the cool part, the derivative of g, which is derivative of the bottom, and the derivative of cosine is negative sine, so I put negative sine x here. And then the formula says times f, f is the top, which is another sine x, and then all of that over the bottom, which is g, but squared. And do y'all see what happens up top?
Yep.
See how that minus minus becomes a plus? And so you have cosine squared x plus sine squared x on top. And that, by the Pythagorean identity, is equal to 1. So we get 1 over cosine squared x, which is the same as 1 over cosine x squared, but 1 over cosine is secant, so this becomes secant x squared, which is why the derivative of tangent is secant squared x. All right. Time for another one. G of t equals t cubed minus t plus 1 over 4 minus t squared plus t to the 5th. Find g prime of t. I'll give you a minute. I'm going to send the poll out again. Tell me when you're done. Okay, so our first person done took 35 seconds. Well, we've got 2 done now. Not that this is a race. So more than half of the class is done now. Okay, I think we're there. Javier, are you there?
Yes, I'm here.
Did you get it yet?
I was almost done.
Okay.
Okay, so first thing I did was I set the numerator as f, right, and the denominator is g. So what I did is for the t cubed, I rewrote it as 2t, and then minus 1. So that's my f prime.
Oh, wait, hold on. Oh, 3t squared? Did you bring the 3 out?
Yeah, that's what I'm saying. I brought the 3 out.
3t squared minus 1. That's your f prime. Yes?
Yes.
Okay, I'm gonna call it, that's your f prime. Now you're gonna multiply that times what?
G.
G, which is gonna be the entire bottom, right? You're not gonna touch it. You're not doing a derivative. You're just leaving it alone.
Right. And then
what?
you're going to subtract it by
Good.
G prime.
Which is?
Should be, okay, minus 2t plus 5t.
Negative 2t plus 5t.
Oh, to the 4th.
To the 4th, good. Okay, good. You're doing good. All right, keep going.
And then we're going to multiply it by f.
Times f, and that's just the numerator. Don't touch it, right?
Right.
Okay, and then all of that, the whole thing, divided by
The denominator squared.
the denominator, just in parentheses, squared. There you go. That's it. Good job. Good, good. All right, we have 19 minutes left. I'm ready to give you a challenge problem now, something that see how you do with this, all right? Any questions before I give you this one?
I have a question about the first one.
This one or the one
Yeah,
before?
the x over sine x.
Okay.
Could you just change it to x times cosecant x and do the product rule?
Yes, good question. You could do that. So the question was, could you take that and rewrite the original function as x cosecant x? Okay, and then take the derivative and then use the product rule, right, instead? So if you did that and did a product rule here, it would be the derivative of the first one, which is 1, times the second one, plus, because it's product rule, derivative of cosecant x. So that you would have to go look back at. So do you know what derivative of cosecant x is? No, you'd have to look on your formula sheets or you have to look on the notes. I'll tell you what it is. It's negative cosecant x cotangent x. That's the derivative. That is the derivative of like if this is f and that's g, that's the derivative of g. And then times, you still have x here. And if you look down here, it matches this. Right? Do you see that that matches? Because you have cosecant x, you have a plus minus, which is going to give you a minus, and then you have cosecant x, cotangent x. We have that here, and then we had an x back here, which is moved to the front. So the answer is yes, you could. Good. Now, there's not, one of them is not more correct than the other. All right? They're equivalent.
So I had a quick question.
Yep.
It's probably not true, but for that tan of x, when you're gonna take the derivative of that, could you put it over 1 to make it f over g?
Yes, you could, but then when you did the formula, right? So I think what you're asking is, could you just look at this as tangent over 1 and then do like, this is f and this is g, right?
Right.
But then when you do the quotient rule, the first step is the derivative of f. So derivative of tangent, you would have to know is secant squared. See what I'm saying?
Yeah.
And I was saying, try and get the derivative of tangent without knowing that it's secant squared. In fact, if you wanted to prove this, you know how I just said right now that the derivative of cosecant of x is this? It's in your formula sheets.
Right.
You could prove that by doing this. Here's a derivative here. If I want derivative of cosecant x, I could do derivative of 1 over sine. And then call this f and call that g. And I promise you, if you do the quotient rule on this, you will get this. I won't do it. I'll just leave that to you if you want to show it.
That's all I had. Thank you.
Okay, good. Good questions. All right, here we go. You ready for this one?
Yeah.
All right, that's some enthusiasm right there. So I'm going to give you a few minutes to think about this one. And hopefully you'll notice pretty quickly that this problem is different. All right. But I'm going to let you think about it for a minute.
Don't we have a product on top?
Okay, so yeah, you're seeing that there's something going on here, right? All right. So just try and think about how you might approach this. I'll help you all out in a minute, but I just want to see if you can kind of find your way through it or not. I'm going to put the poll out there again because I want to know, like maybe somebody, you know, some of you have done some calculus, so you might be able to get it. Okay, I think we're going to take a minute to talk about this. So what I want to say first, what I want to show you first is one of the more common incorrect answers. All right. I hate showing the wrong way to do something, but in something like this, I think it's instructive. So here's something that is not correct. All right, so let me see who's up. Elise, how's it going?
Hi, good. How are you?
So did you feel like you got it?
Yes, sir.
Okay, so do you see the work I did? Can you tell me why that's not right? Like what I did wrong?
Because can you hear me?
I can hear you, yeah.
Because you're missing the rest of the quotient rule.
Okay, so from what I'm showing there, what did I do up top?
You only took the derivative of the numerator.
I just did the derivative of the top by itself, right? Now I did a product rule, didn't I?
Yes.
But I still just did the derivative of the top and then the bottom separately. And you're not allowed to do that. Okay. I agree that the numerator is a product, but ultimately that product lives within a quotient. So what you have to do is you have to separate the numerator call that F, and call this entire thing G. And then you run the quotient rule. So Elise, you want to take us through that?
Sure.
Well, yeah, I mean, yeah, tell me what I'm going to do. Don't tell me the answer, but tell me what I'm going to put, like what goes first here.
So what would go first would be the derivative of f, which
Okay,
would be
I'm going to write that
using
down.
the product rule.
Yep, so I'm going to, Elise is saying that what goes in the top left here, going off the quotient rule. Quotient rule says if you have f over g and you take derivative, it's going to be derivative of f times g minus derivative of g times f all over g squared, right? That's the formula. So Elise is saying that whatever the numerator is, we need to take its derivative. So here's the way I'm going to write that. I'm going to write x squared sine x, but I still need to take its derivative, right? So I'm going to put prime. Now, Elise, what am I going to multiply that by?
The denominator, the bottom.
Just the denominator, right? Okay. And then subtract, right? And then what do I put? What's going to come next?
Derivative of the bottom.
The derivative of the bottom, which I'm going to put x cubed plus x, and I'm not going to take derivative yet, so I'm just going to put a prime mark that reminds me I still need to take the derivative of that. And then what?
And then just the top.
Just the top times the x squared sine x. And then all of that over
the bottom squared.
Bottom squared. So the whole thing on the bottom squared. Are there any questions on this setup? We're not done, okay? But this is the setup. We have quotient rule happening here. F prime is here, right? G is here. G prime is here. And then I'm going to run out of colors. That's F, right? But see, we still have to take two derivatives, don't we? We have to take derivative of this. That one should be easy, right, Elise? What's the derivative of x cubed plus x?
3x squared plus 1.
3x squared plus 1. We should be able to do that mentally. This one, however, is a product rule. Do y'all see that? That's where we're going to have to do the product rule. On that yellow step, we have to do product rules. So maybe for you, that means, and I'm not saying Elise, but maybe for you, because you're just new to all this, what you might need to do is on the side, you might need to do some scratch work, SW, scratch work. You might actually have to come over here and separately go figure out what the derivative of this is using the product rule. And when you run the product rule on this, calling this f and g, then you get 2x sine x plus cosine x times x squared. Are there any questions on what I'm doing over here? Trying to figure out the yellow, but I don't feel like trying to do it all here, so I'm just going to go figure out what it is here, and then I'm going to go slap that answer in here. So Elise, do you want to give us the final version, or?
Sure.
Yeah, go ahead. So let's just read it out. What do you got?
And the numerator, between parentheses, since we're multiplying, it will be 2x sine x plus x squared times cosine x. And then that all will be multiplied by x to the third plus x. And then minus x squared sine x.
Oh, okay, you did it the other way.
Yeah, I did. I reversed it.
I'm going to leave mine. I'm going to leave mine the way I have it, just because this is the way I'm presenting it. But it doesn't matter because it's multiplication, right? So you can switch the order.
Then all that divided by x to the third plus x squared.
There you go. There we go. What do y'all think? Do y'all have any questions on that? So what's happening here is that everybody's happy because we have these rules, right? Like, oh, now we've got these rules. We don't have to do the limit anymore, and you're all excited about it. And now what happens is instead of you having to suffer with the limit, now the functions become more complicated, right? And so now when you take the derivative, like in this example, we had quotient rule, but within the quotient rule, we had product rules happening, right? Right? So, I mean, imagine a problem I could give you like this. Why don't we make this a take-home problem just for you to do for fun and for practice? How about if I gave you something like, I don't know, x tan x over x plus 1 sine x. So do y'all see that, again, we have like, ultimately we have a quotient rule that we have to run. But do you see that in the numerator, you'll have to run a product rule? And in the denominator, you have another product rule? Do y'all see that? So things are going to start to get ugly pretty quickly here, all right?
So
I'll leave that as a fun problem for you. Question?
For problems like this,
Yeah.
you want to do the quotient first, and then
Yes.
you add in the product rule.
That's right. You
Okay.
you just kind of say, everything up here is my F. Everything down here is my G. And now when I do my F prime G, quotient rule, minus G prime F all over G squared, when I do that, when I get to this F prime stage of the formula, I've got to take derivative of that. That's when I bring the product rule in. And then when I get to the G prime, that's when I bring in the product rule for these two. That makes sense, Benjamin?
Yeah, I was just confused on the order of operations.
Yeah, that division bar is what you look at first, because that's the main thing happening here is that you have a quotient.
Okay, because that mistake that you demonstrated, I did that.
Okay, yeah, good. So I'm glad that you did. Now you know you can't just do them separately like that.
Okay, thank you.
Good. All right, so I have 4 minutes. I just want to point something out to everybody. If you were to go look at the formulas that come from the book, here are the formulas that come out of this textbook. So let me try and illustrate what these formulas are saying. Here it's saying you're taking the derivative of f of x times g of x. So what all of this really means to us is f times g, take the derivative. Do you all see that that notation means the same thing as this? Take two functions, multiply them, take their derivative. Is that okay?
Yeah.
Now look at their version of the formula here. They have f times g prime plus g times f prime. That is the way that the book presents the formula. Is that the way I presented it? No, right?
No.
What did I do? I said, no, I don't like this. I did these two guys first, and I changed their order. So I put f prime in front of g, and then I did plus, and then I did these two, but I put the g prime in front of the f, and I put g prime f. But do y'all see it's the same thing? Because with addition, you can change the order, and with multiplication, you can flip the order, right? So you might ask yourself why I did that, right? Like, why would I present that formula instead of the one the book does? Well, just bear with me for a minute. I still have 2 minutes. Look at the bottom formula. This means take f over g and take its derivative, right? That's what this means. Take a quotient of two functions, take their derivative, and look at their formula. It's g times f prime minus f times g prime all over g squared. Do y'all see that? So when I was a student, right, of calculus, my textbook that I learned from did this the exact same way as this textbook. And there's something that I hate about this, and that is, do y'all agree that this formula here and this formula here look like they're almost completely different formulas? Like, this one is fg prime plus gf prime. This one is gf prime minus fg prime. Seems like if I had to memorize that or something, it would be, it seems like I would get this mixed up a lot. Does that make sense?
Mm-hmm.
But if you look at it the way I presented it to you, all you have to do is memorize that. And then when you go for the quotient rule, it's the same formula with a minus between over g squared. And so these two look very much the same, don't they now, as opposed to these two? I don't know. If you're following me, great. If you're not, don't worry about it. Just memorize these two. And I'm only saying this because I can always tell the students who have learned the formula this way, these two ways. I can always tell the students who have been in another calculus class, because they continue to give me derivatives this way instead of the way that I'm showing you. But I think that it's more, I think it's just easier to memorize this way. That's just personal. I don't care what you do as long as it's right. but I want you to know why I'm doing it, like the motivation for me changing the way the formula is being presented to you. All right. Well, what are we doing? We're going to have spring break, right? So over spring break, I would expect that you attempt to do the homework for, where are we? We're up through, we have now done the basic differentiation formulas, and we have talked about the product and quotient rules. There's no new rule I need to give you. I mean, like for 2.3 and 2.4, you have all the rules you need to attempt to do the problems. Now, that doesn't mean you're going to be able to get through all of them easily, but I would say at this point, we are through all that. So you should try and take your spring break to get to a point where you are up through 2.4. And when we return, I will kind of recap where we were, and then we will get right into the chain rule. And the chain rule is the most important rule. And it's basically the one you're gonna live or die by. You learn the chain rule and you're gonna move on, and calculus 2 is gonna go much better for you. If you struggle with chain rule, then this is where you hit a wall, okay, in this class. Now, everyone here is capable of doing it. I'm just telling you, 2.5 is like the section that you have to understand. But you can't do chain rule. You have to be able to do basic and product and quotient. Can't do chain without those, right? So the foundation is laid. Chain rule comes when we come back. Everyone have a safe holiday, and I'll hang out for a minute if you have a question.
Hey,
Yeah.
Professor,
Okay.
I do have a quick question. So I was wondering, since we did a product rule right on the last one,
Mhm.
product rule and a quotient rule. So for a product one, since we're just